The first pulsar was detected by Jocelyn Bell under the supervision of Anthony Hewish in 1967. She detected pulses of radiation separated very regularly by 1.33 seconds. They nicknamed this signal LGM, standing for Little Green Men, because the regularity was so unusual that it suggested an alien origin. When the next pulsar was detected coming from a completely different part of the sky and with a different time separation, the alien idea was abandoned completely. In fact, pulsars are rapidly rotating neutron stars with extraordinarily large magnetic fields, which are left behind after supernova explosions. And they spin so rapidly because they form from the contracting core of a star before it goes supernova. And the core must spin faster to conserve angular momentum. And this is just the same as how an ice skater will spin faster when they bring in their arms. And if you search scratch spin on YouTube, you'll see what I mean. And by the time the core of the star, before it goes supernova, has finished contracting to leave behind a neutron star, it is extraordinarily dense. If the Earth were compressed to neutron star density, it would have a radius of just 150 meters. Or something the size of this pea would have a mass of 26 million tons. Also, in a pulsar, the magnetic and rotational axes are misaligned. So if we imagine that this orange is a pulsar, then these normal cocktail sticks are its rotational axis, so it rotates around like this. And then these black cocktail sticks represent its magnetic field axis. And this is important because in a pulsar, beams of light emerge from the poles of this magnetic axis here. And we only detect a pulsation from a pulsar when its beam of light is directed straight towards us like this. And you can see that that only happens periodically because the pulsar rotates around on its rotational axis like this. So this is why we see periodic pulsations from pulsars. I asked Dr. Cameron Rolton to tell me more about pulsars.
So you get these huge swathes that sort of brush out, these waves that brush out.
Okay.
And when we're here on Earth, somewhere down, wherever we are, down here,
Yeah.
so this in effect is almost like these pulses arrive in waves as they sweep across the interstellar space.
Okay.
And then that's what we detect as these kind of the pulses, and they
Yeah.
arrive in set intervals.
In fact, the regularity with which we receive these pulsations is extraordinary. Their precision rivals the best atomic clocks that we can make on Earth. And these best clocks won't gain or lose a second in tens of millions of years. We receive light from across the electromagnetic spectrum in the pulses. And although our models struggle to explain it, we even see pulsed gamma ray radiation from some pulsars.
So what Veritas are saying is that they've seen pulsed gamma radiation coming at energies way higher than anyone had predicted, right? So this was a huge surprise.
Objects in space are analysed by looking at their energy spectra, which we draw on a graph like this. So on the y-axis is increasing flux, which is the number of photons you detect per second and per area. And then along the x-axis is increasing energy. So here on the graph we've got high flux, so we detect lots of photons, but they have quite low energy. Whereas over here, say, we have a low flux, so we don't detect many photons, but they have a high energy. Cameron told me more about the energy spectra of pulsars.
So when you look at the energy spectra of these things, so at around a few GeV here, you should get the sharp drop off like that, right? It's been suggested that with the observations of gamma ray pulsars by the Fermi Gamma Ray Space Telescope, that there's an apparent absence of this kind of really sharp cutoff in the energy spectra.
Fermi has made a great contribution to pulsar science. It's brought the number of detected gamma ray pulsars from 7 to over 100. But the absence of this really sharp cutoff in the energy spectra just mentioned, and the discovery of so many of these gamma-ray pulsars, means we need to observe pulsars in greater detail so that we can better understand these objects and so we can make our models better fit what we see.
So what CTA will be able to do is it'll be able to explore this energy regime in much greater detail essentially than what Fermi is able to do.
Okay. So by exploring this important energy region, the CTA will help us to develop our models of pulsars more accurately. The CTA will also detect gamma rays from the pulsar wind nebulae, and this is a cloud of gas and dust around the pulsar which is made up of the supernova remnants and some interstellar gas. This is the Crab Nebula, the archetypal pulsar wind nebulae. The central pulsar drives the formation of this structure, but is only very tiny in this picture. The CTA should also be able to help us further understand particle acceleration in these pulsar wind nebulae.